Good afternoon. My name is Karla. I'm an undergraduate physics student, and today I'm going to present my research work that is theoretical and simulation study of gamma-initiated particle showers in the atmosphere. In the present work, simulations study the development of particle showers generated by photons as primary cosmic rays were carried out. We aim to determine whether or not it's possible to detect a gamma ray burst generated by an external source to the Earth with a water Cherenkov detector placed at 4,600 meters above sea level. We compare the results of the simulation with the theoretical models that describe the behavior of the showers at the detector level. In addition, we will be able to establish the properties of a detector to be implemented in the future. We use ARI, the LAGO-Corsica simulation chain, in order to generate the gamma-initiated particle showers in the atmosphere to obtain the information of the secondary particles that reach this site of the study. To simulate the showers generated by gamma rays, the LAGO-Corsica package was used. The input parameters to consider were the primary energy and the type of the primary particle, the zenith angle and azimuth angle, the level of observation, and the atmosphere model. We need to filter accurately the data obtained from the simulation before we analyze it. For this, a script written in Python and root was used, so we could get a better filtered data with the components that we would use for the plotting. After that, we're going to calculate the mean number of the secondary particles of each type that reach the observation level versus each primary energy of the primary particle and the density of the lateral distribution. The following graph shows the mean number of secondary particles that reach the observation level versus the energy of the primary particle for zenith angles of 0 and 30 degrees. From this graph, the first thing that can be seen is that the higher the energy of the particle is, the mean number of particles is also higher. Also, we compare the development of vertical showers with the ones slanted at 30 degrees of zenith angles. The mean number of all secondary particles reaching the observation level versus the primary energy for these two angles of injection is also displayed in this figure. And a slightly difference is observed between these two angles, which means that high-attitude surface detectors are very sensitive to the primary particle injection angle of 0 degrees with respect to an angle of 30 degrees. Next graph of lateral distributions of secondary particles are presented versus the radial with respect to the axis of the shower. For two energies that are 1 giga-electron volts and 100 giga-electron volts. What can be seen here is that the higher the primary energy is, there is a great number of particles per square centimeter, and this density is more concentrated around the points closest to the axis of the shower. Now, comparing for the same primary energy, there are two components, an electromagnetic component and a muonic. The density and dispersion in the electromagnetic component is higher than the muonic component. In this case, we have the same analysis done previously, but for different energies of primary particles. These are 500 giga-electron volts and 1 tera-electron volts. In this case, the detection of GRVs with water Cherenkov detectors is powered by the presence of high energy pairs into the water created by photons, able to produce Cherenkov emission. Therefore, through this work, we can say that the future detector to be installed at such height should have a radius equal to 300 centimeters. Furthermore, it will be very convenient to find sources of GRBs whose photons generated when entering the air atmosphere have a zenith angle of 0 degrees, since they have a created mean number of secondary particles that when it's 30 decrease. Additionally, it will be good to do a study of the energy distribution for the first beam, since this would help us to finally decide if the photons that can reach the level of observation have enough energy whose created particles, whose created pairs would be able to emit Cherenkov radiation. Thank you.